All right, in this example, we have an unknown quantity k, and we're going to see what happens when, once we've set up the matrix equation, what kind of solutions we actually get. So we've got three different values of k for this. So I'm just going to write down what the matrix A would be in this situation. So looking at the coefficients, we've got 3, negative k, negative 6. Okay, these are just the coefficients, of course, of the variables. So we've got k, 3 and 3 for that second row, and then we've got negative 3, negative, not negative y, sorry, negative 1, and 3 for that third row. Okay, all of this will be multiplying the three-dimensional column vector x, y, z, and the solution on the right-hand side of our equation will be k, 2, and negative 2. All right, so our job now is to figure out what happens in each of these situations. We've got k equals 0, first of all, to consider. Now, what we'll need to do is we'll need to figure out the determinants of this matrix. So I'm going to call this matrix A right here, just so we've got something to refer back to. So for the determinants, I'm going to do the determinant in the top left up here. For the determinant of A, well, we've got to use our technique that we saw in an earlier example. So I'm going to highlight the first row. I'm also going to, I would say, highlight the first column. I'm going to highlight the first row. And then we're going to find the determinant of the minor here and the cofactor 3. So we've got 3 multiplied by the determinant of 3, 3, negative 1, and 3. Okay, for the next part, we're just going to move that over there. We're going to cover up the first row and the second column this time. And we're going to calculate the determinant of that minor that's left over. Now, bear in mind, of course, we've got negative k here. This is going to become a plus k. So I'm just going to highlight that. So it's going to be plus k there because we have to alternate the signs. There's lots to remember with this. Just so you recall, it goes positive, negative there, and then positive. So that's what I've done here. I've got the plus sign right here. Let's put that determinant in. So the determinant of the minor, which is going to be k, 3, negative 3, and 3. And then the final term is going to be negative 6. And then let's just move that over, that highlighted part. We're eliminating the first row and the third column this time. And the minor that we have left over is going to be k, 3, negative 3, and negative 1. All right, so we're going to compute that. I'm just going to move all this down to the bottom. So therefore, the determinant of A, and we're going to get some algebraic expression here in terms of k. Well, we've got 3. I'm going to open up a bracket to calculate the determinant of that first minor. So once again, we multiply the leading column together and we subtract the product of the non-leading column. If I do that, I'm going to get 9 subtract negative 3. So that's 9 plus 3, which is, of course, 12. That's going to go in there. Let's change back to blue there. Okay, and then we've got plus k. And this time, that's going to be multiplying 3k for the product of the leading diagonal in that second term. Subtract negative 3 times 3, which is plus 9. Okay, and then the final term is negative 6 multiplying negative k, and it's going to be plus 9 again. All right, so we're going to tidy up this algebra. So we've got 3 times 12, which is 36. Expand the bracket, plus 3k squared, plus 9k. Okay, and then we've got double negative there, so that's going to be plus 6k. subtract 6 times 9, which is 54. Okay, so we've got a quadratic. Last line here now. So just bringing everything together, we're going to have 3k squared plus, now putting the k's together, we've got 15k altogether, 9 plus 6, and then 36 subtract 54, that's going to be negative 18. All right, so we've got this quadratic expression for the determinant of the matrix A, and obviously k is going to vary in each of these scenarios. So let's have a look at scenario 1, which is k is equal to 0. So for part A, when k is equal to 0, what we have is that the determinant of A is simply going to be negative 18. Now, this is important because this is a non-zero determinant. So this is non-singular, does not equal to 0. So when k is equal to 0, A is a non-singular matrix. So this means that there is a unique solution. Okay, now we're going to have a look at the geometric implications of that next. All right, so there's various scenarios that can happen when we have singular and non-singular matrix. We've just computed a non-singular matrix when k is equal to 0. We got a determinant that was negative 18. This is the only case which presents a unique solution. So it means that the three planes, now the three planes I'm going to just talk about briefly. If you have an equation of this form, so if you have an equation of the form ax plus by plus cz, where your variables are x, y, and z, is equal to some other constant d, this is the equation of a surface, so or a plane. So imagine some kind of two-dimensional surface like that. I'm not drawing that particularly well, but that's what that equation describes, because we need to have a position described in 3 dimensions. Okay, when the matrix is non-singular, that means that you have 3 of these planes all intersecting at one unique point. Okay, so let's move on to the next 2 cases. We've got to consider k when it is a different value next. So now let's have a look at the situation where k is equal to 1. Well, for part B, the determinant of A when k is equal to 1 is going to be 3 plus 15 subtract 18. Now you can see straight away this is going to give a determinant of 0. So in this situation, when k is equal to 1, A is singular, which means that we're not going to get a unique set of solutions this time. Let's see what we do get. So if I apply this matrix to the variables x, y, and z, so we're going to have 3x subtract, now k is 1, so subtract y, subtract 6z, and then we've got x, k is 1, of course, plus 3y plus 3z, and then negative 3x subtract y plus 3z, like that. Now, all that has got to be equal to the right-hand side of the equation. And I'm just going to have to check that because I can't remember what it was. K2 and negative 2. let's have a look at that. So k is 1 in this case, so it's going to be equal to 1, 2, and negative 2. All right. Now let's try and solve these three equations. So let's see how far we get with this. So this is equation 1, this is equation 2, and this is equation 3. Now you'll notice to solve this, we've got to eliminate 2 out of the 3 variables essentially. Now you'll notice here we've got 3z in equation 3 and 3z in equation 2. So I could do equation 2 minus equation 3 just to get us started. So let's start with that. 2 subtract 3. And what we're going to get here. Right, so we're going to get 4x. Just being careful with the signs there. Plus 4y. Okay, the z's will clear, and that's going to equal 2 subtract negative 2, which is of course 4. All right, so can cancel the 4's out, so we get x plus y is equal to 1. Now that could be, we'll call this equation 4. So we've generated a new equation now with no z involved. Right, what else could we do? Let's try and eliminate z from the first equation here. Okay, so this time if I double my equation 2, I'm just going to write that down. So that's going to give me 2x plus 6y plus 6z is going to equal 4. So that's equation 2 doubled. Okay. Now let's look at what we can do now. If I take equation 1 right here, and I probably should have done that in a different color so we can see it. So equation 1 right here, and combine that with equation 2 to try and eliminate the z variable, I can simply add them together. So if I add them together, I'm going to get 4x again, minus y or negative y plus, oh, that's wrong. I'm sorry, I'm looking at the wrong one. It's going to be 3x plus the 2x, which is 5x, of course. Then we've got negative y here, plus 6y, so that's plus 5y. This negative 6z and the plus 6z here will cancel. And then we've got equals 5. So once again, we get this time x plus y is equal to 1. Right, now that means that we can't solve this simply because we've got 2 variables. There's no way I can eliminate either x or y in this situation. This is all we're going to be left with. This is a straight line, so it means that I'll just rearrange it to make it a bit more familiar. So this is y is equal to negative x plus 1. This is a straight line, so these 3 planes intersect along this straight line here. Y is equal to negative x plus 1. So which geometric arrangement does this correspond to? Okay, so in this situation, we have a line which represents the points of intersection. So it's an infinite set of points. So it's consistent because we found no issues with eliminating the z variable. Okay, and the 2 equations that were remaining were, in fact, x plus y is equal to 1. What we did find, though, is that's it. So if that's the point of intersection and it's an infinite set, well, it's an infinite set of points, isn't it? It's going to be a sheaf because it's this line here. where the three planes coincide. The three equations don't represent the same plane. That's clearly true because they weren't the same equations at all. And we've ruled out there being a unique solution because the determinant was 0. So it's consistent and we're going to get a sheaf in that case. So for part C, we've got k is equal to -6 in this situation. Now, once again, if we substitute k into our determinant right here, okay, and evaluate that, I'll save you the trouble. We're going to get 0 again. So we've got the two solutions to the equation det A is equal to 0, essentially. One of them is -6. So we'll get det A is equal to 0. That means this is a singular matrix again. So there's various things that can happen when you have a singular matrix. So let's explore what's going to happen if we try and solve this system of equations here, where k is equal to -6, and see if we can deduce what the geometric form would be. Okay, so I've written out the system of equations for this situation, and you can see straight away, if I have 3x and -3x in equations 1 and 3, let's add them together and see what we get. So we got 1, didn't like that 1, let me try again. So we've got 1 plus 3, and this will eliminate the x variable this time. It doesn't matter which one you want to eliminate, it's completely fine. So we're going to get 5y. We've got, we're adding, so we've got subtract 3z is equal to -8. Okay, so we've eliminated x this time. Now we can also eliminate x a different way. We could take equation 1 or 3 and multiply it by 2. I'm going to take equation 1 actually. So we're going to multiply that by 2. And that's going to give me 6x plus 12y subtract 12z is equal to -12. So that's equation number 1 multiplied by 2. Nothing wrong with that because we're not changing the nature of the equation whatsoever. We're just scaling the coefficients up, which is absolutely fine. Right, now let's have a look what we've got in this situation. If I take equation 2 this time, so equation 2, and I'm going to add 2 lots of equation 1. Now let's have a look what we get. So in this situation, we've got equation 2, which is -6x. I'm going to change that color again. I don't like it. Let's go back to green. So -6x there, plus 2 lots of equation 1. So plus that, that's just going to cancel out the x's, which is what we want. Right, let's do that. So there's going to be no x's whatsoever. Now, if I take equation 2 and then I add 2 lots of equation 1, I'm going to get 18y because I've got plus 3y plus 12. Why did I write 18? That was stupid, wasn't it? Not 18. That's going to be 15y. All right. And then looking at the z's, we've got plus 3z subtract 12z. Okay, so we've got subtract 9z, and then we do the same thing with the constant. So we've got 2 subtract 12, which is -10. Right. So we've got 2 completely new equations. We've got 5y subtract 3z is equal to -8. Let's just highlight that. So that's our first equation. And we've got 15y subtract 9z is equal to -10. Now, if we try and solve this, I can multiply that first equation right here by 3. And then if I write this up here, we're going to get 15 y subtract 9z is equal to 3 lots of minus 24. And then I've got 15y subtract 9z is equal to negative 10. So those are my two equations. So I'm just solving as much as possible until this system breaks down. We know it's a singular matrix. This is not going to work. And straight away, as you can see, if I subtract, let's say if I do 4 subtract 5, the 15y's are knocked out, the 9z's are knocked out, but then we get a contradiction. That we get 0 is equal to 24 plus 10, which is going to be negative 14, which cannot happen. So this is inconsistent. Okay. Because we can't solve this. So let's have a look at the geometric implications of this now. Finish this off. Let's have a look at those equations again and compare them to our geometric situation. So geometrically, we've got we know we've got an inconsistency, so we know there's no solutions. Now there's 3 options here. We've either got 2 parallel non-identical planes, which don't intersect at a unique point or at a unique straight line like we saw previously. We could have 3 parallel planes, or the planes are not parallel, so they intersect to form a prism shape. Now, we just need to check whether there's any parallel lines in these planes. Now, the way to do that is just to have a look at the coefficients. Now, if it was a case where these lines were parallel, then we would see that one equation would be a multiple of the other. So can we identify that? Well, if we look at the first one, it's a possibility that looking at the first coefficient here, let's just get onto a yellow color, I think. Oops, didn't want to do that either. Let's put that back. All right, so looking at the coefficient here, it looks like, if I can compare those, it looks like we've got a multiplication factor of -2, but you can also see that this doesn't hold when we look at the coefficients of y. So these lines are not parallel. Similarly, I've got -3 there. If I can compare that one to equation 2 right here, it looks like I've multiplied here by 2. But once again, this doesn't hold when we look at the coefficients here. So we don't have any parallel lines whatsoever. The only way we have an inconsistency without 3 parallel planes is this third option here, where the planes intersect to form a prism. So there's no solutions and there's no parallel lines at all.